My name is Casey Burleyson. I'm a PhD student at North Carolina State University, and my research focuses on clouds and drizzle. So marine stratocumulus clouds are low liquid phase clouds that occur over the open ocean. And they're very interesting for a number of reasons. One of the reasons is they're very, very persistent. So this is a plot that Dennis Hartmann did in the 1990s. And what it is, it's a global distribution of the low cloud fraction. So you have cooler colors means less cloudy, warmer colors means more cloudy. And if you look at the plot, sort of three areas stand out off the coast of South Africa, South America, and off the southern coast of California down here. And what these are large sheets of marine stratocumulus clouds. So they're very, very persistent. They have a cloud fraction on the order of 70% of the time. And they cover very, very large areas. And the properties of these clouds are sort of unique because they're low, in that they actually reflect a lot of incoming solar radiation. So this is just another follow-up plot by Dennis Hartmann where we show the net cloud radiative forcing. So what that means is the difference that the cloud makes in how much sunlight is actually reaching the surface. So if you take your eye to the three marine stratocumulus regions, you see that they have these very, very red and orange colors. And what this indicates is they're reflecting lots and lots of incoming shortwave radiation. So these low clouds have a very important role to play in the radiative balance of the climate because they reflect lots of radiation. One way to look at this is this plot that the IPCC made in their fourth assessment report, which came out in 2007. And there's a lot of different things going on in the plot, but I'll just draw your eye to a couple of them. On the x-axis is the radiative forcing. So the zero line runs right up through here. Everything to the right of the zero line means warming, and everything to the left of the zero line means cooling. And along the y-axis here we have all the different forcing terms. So greenhouse gases are at the very top, CO2 up here. You can see that it has a large warming impact on the radiative balance of the climate. But if you go down the list, you'll see these two kind of blue bars that go into the negative region down here. So these have a net cooling effect on the climate. And what these two bars are what's called the direct and indirect effects of the radiative forcing from low marine clouds. So these two bars capture the cooling that these clouds have on our climate as a whole, and they affect the net radiative forcing of the climate, which is this red bar at the bottom. So the IPCC in all their simulations, the red bar was strongly positive on the order of, say, 1.5 watts to 2 watts per meter squared. But the cooling effect of these clouds is such that it sort of mitigates some of the warming. But the important part here is the error bars on here. And I don't know if you can see it, maybe we can zoom in on the video. The error bars are given by these black lines, and this shows the region between the 25th and 75th percentile of the forcing. And the CO2, the error bar is relatively small. Surface albedo, the error bar is relatively small. When you get down to these cloud radiative impacts, the error bar jumps up. It's huge. It's almost like a full 1.5 watts per meter squared. So this is a lot of uncertainty. And if you look at the error bar for the total radiative forcing, almost all of it can be made up of just the error from the cloud radiative forcing from these low clouds. But we know that they have a cooling effect, but the error bars are such that we don't know how much cooling they're actually having to offset the CO2. So I think it's important to point out here that even if it has the maximum amount of cooling, we still have positive warming from the CO2. So this doesn't say that global climate change or global warming isn't going to exist. It's just a question of is it going to be 2 watts per meter squared, which would be on the upper order of 4 to 5 degrees Celsius warming, or is it going to be down towards 0.5 watt per meter squared, which would be, say, maybe 1 degree Celsius warming. So this is a lot of uncertainty. If you think about it, the best analogy that I've heard was if you were living in New York and your company told you that you were going to relocate to the West Coast, and they gave you a compass and they said, get in your car and drive to the West Coast. The error on this cloud effect is such that you may end up in Alaska or your compass may point you all the way down to San Diego. So you're going to get there, you're going to get to the west coast, you're going to get a warm scenario, but you don't know how warm it's actually going to be. And this is a big problem. This is something that we as a science community have sort of shifted our focus towards, and it's driving a lot of research, which is very good for me as a graduate student. So one way to look at this is to see how our global climate models do at capturing the radiative impacts of these low clouds. And in order to get the radiative impacts right, they have to get the cloud fraction right. So if you take the bottom panel down here as the truth, this is from a satellite, a MODIS satellite shot done by Matt Wyant at University of Washington. Red colors means higher cloud fraction, cooler colors means lower cloud fraction. So if this is the truth, we can look at how all these different global climate models do trying to get this accurately, and you can see there's a lot of spread here. So our global climate models aren't capturing the cloud fraction correctly, so they're probably not getting the radiative impacts right either. Now there are a couple that do better jobs than others. Say ECMWF is down here in the lower left corner. It does pretty well, but some of them are way off in left field. And this is a problem. It's not necessarily the modeler's fault, because they have a very challenging problem in modeling marine stratocumulus clouds. A lot of times in weather research, you can sort of focus your area on one specific process or types of processes. Like some people are synoptic meteorologists, so they'll study synoptic processes. In our group, we're precipitation meteorologists and cloud physicists. The problem with marine stratocumulus is all of those things merge together, so that you can't discount anything. You have to account for all these different processes. So we're talking cloud physics, boundary layer processes, mesoscale processes, synoptic scale processes, aerosols, and the list goes on and on and on. So from a modeling perspective, they're trying to get all of these different things that are interfering with each other and modifying each other, and trying to get their model to converge to the right solution. That's a very challenging thing. So someone gave this analogy, and I thought it was really apt. In a global climate model, the average grid box would be about the area of the interior of the Raleigh Beltline. So a lot of people live in Raleigh, and they know how big the Beltline is, and how much area it encompasses. So one model grid box is that. So from a modeling perspective, they have to capture processes that are going on in the whole grid box, and they have to capture processes all the way down to the scale of a cloud particle, which is infinitesimally small or microscopic. So this is a very challenging thing for models to do, and they're really struggling. So that's where we come in.